In part 5, we have a bunch of equations to solve. And they're all mixed together. These equations could be logarithmic, could be trigonometric, exponential, could be anything. So let's get started and see if we can parse which ones are which. The first equation we have has a logarithm in it, so we know our goal. We know our goal is to get the logarithm by itself on one side, and so again, I won't show every step here because I don't have much room, but I'll subtract 4 from both sides, and I'll divide both sides by 2. If you do those two steps, you'll have the natural log of x plus 1 equals negative 2. Now we trade that in. Remember, natural log is really log base e, so I'm going to trade that for an exponential equation in base e, but the input and output are swapped. So instead of the x plus 1 going into the function and minus 2 coming out, minus 2 goes into the function and x plus 1 comes out. So we've interchanged the input and output when we change from log base e to exponential base e. And after that, it's easy to solve. So x will be e to the minus 2 minus 1. The second equation is an exponential equation, and so we know we want to try to get our exponents all together on one side, or our terms that have the terms that have the variables in them on one side. But you may notice that all the bases here are either 3's or could be written as 3's. So that's never a bad idea. That'll allow us to avoid introducing logarithms if we can have both sides written as powers of the same base. So if I rewrite 9 as 3 to the 2x, that is writing 9 as 3 squared to the x and multiplying the exponents, then it will become this equation. And now this fraction on the right-hand side, that's 3 to the 2x divided by 3 to the first, and so I know I subtract exponents. So this equation can be rewritten without really doing a lot of work, rewritten in this form, and because those are both bases, both exponential expressions of base 3, then that means the exponents have to be equal, and I can avoid having to mention logarithms in this case. So I'll have 2 minus x equals 2x minus 1, and again, if I add 1 to both sides, add x to both sides, I can do that game, but I'll end up with x equals 1 as my final answer. In part C, we see we have a trigonometric equation, and now we have to shift our gears and say, okay, well, in trig functions, I want to get my trig function by itself on one side. So if I do that by adding 1 and dividing by 2 on both sides, I'll have sine squared of x equals a half. Then I have to take the square root of both sides, but I have to be careful. There's going to be two cases. Sine x could be the square root of a half, or it could be negative square root of a half. So there are two different problems to consider. One thing that's important here is to recognize that the square root of a half is really our old friend square root of 2 over 2. So it really is one of our table values. So the sine of x, when the sine of x is a half, square root of a half, that's really square root of 2 over 2. That means that from our table, x would be pi over 4, or by symmetry, we know that if we have one solution to a sine equation, then pi minus that answer will be a second solution. So x being pi over 4 or 3 pi over 4 will both be solutions to the equation sine of x equals square root of 2 over 2. And similarly, let's put a double bar here so we can keep track that we separated this. The sine of x being negative square root of 2 over 2 is going to lead to the solutions x equal, the table will say minus pi over 4. That's a fourth quadrant angle. And then symmetry will be pi minus that, which will be pi over 4. So just on the unit circle, there's actually one solution to this in every quadrant. Pi over 4 is in the first quadrant, 3 pi over 4 in the second quadrant, 5 pi over 4 in the third quadrant. Of course, negative pi over 4 is just a funky way of giving us a fourth quadrant angle. So there's a solution to this in each quadrant. If in these problems, we're trying to describe all solutions, even when they're trig functions, and so for each one is going to get a plus 2 pi k tacked on to describe all solutions. There is no weird thing going on with the x's. That really will be the final answer. So x will be either pi over 4 plus 2 pi k or 3 pi over 4 plus 2 pi k, or so on. So each one of those 4 answers should get a plus 2 pi k, and then we will have described all possible solutions to that equation. In part D, we're doing exponential equations again. So once again, I want to get the term where my x is stuck, this guy, by itself on one side, which in this case I can do just by dividing both sides by 2. And then I'm going to change this into logarithmic notation. Instead of a base 10 exponential expression, which is what I have, I'm going to change it into a base 10 log expression. And the only thing that happens is inputs and outputs get swapped. So instead of input 1 minus 2x and output 2, we have input 2 and output 1 minus 2x in the log expression. But of course log base 10 of 2 is just a number, so I can subtract 1 from both sides, divide both sides by negative 2, and I'll have x is, and I'm going to simplify this, 1 minus log 10 base 10 of 2 over 2. And that'll be my exact answer. In part E, we have a little bit of work to do with our log properties before we even get started, but we still want to start with the same basic idea. I want my log stuff to be by itself on one side. So I'm just going to write log here instead of log base 10, it'll be easier. So if I subtract the log of x minus 7 from both sides, I'll have this expression. The rationale for doing that is that I know a log property that says the log of a minus the log of b is just the log of the quotient of a and b. So I can rewrite this equation as the log of 8x plus 3 over x minus 7 equals 1. And now I do have the expression so that I have a single logarithmic expression on one side and one on the other, which means I can now change this into exponential form. So instead of a logarithmic equation with base 10, I could make this an exponential equation with base 10, where the inputs and outputs have swapped places. So the equation with the logs is equivalent to the equation here with 10 to a power. So I can multiply both sides by x minus 7. On the left I'll have 10x minus 70, and on the right I'll have 8x plus 3. Subtract 8x from both sides, and I'll have 2x on the left. Add 70 to both sides, I have 73 on the right, and so x will be 73 over 2. In part F, we're doing another question with trig expressions. So I know I need to get my trig expression by itself on one side, and that will be sine of x is negative square root of 3 over 2. We use our table to get our first value. In the table, if you look up negative square root of 3 over 2, you find that x has to be negative pi over 3. We know that there's a symmetric solution, which comes from doing pi minus that. Remember, for the sine function, the symmetric solution is pi minus the one that the inverse sign gives us. So pi minus negative pi over 3 is 4 pi over 3. And because we want all solutions, we'll add plus 2 pi k onto each one. In part G, we're trying to solve an exponential equation. The x is stuck up inside the exponent with base e, and so I don't have to do any work at all to get that expression by itself on one side. It already is. So I'm going to right away change this into logarithmic form. So instead of an exponential of base e, I'm going to write this as a logarithm of base e, which is just our ln, but the input's going to be 9 and the output's going to be x squared instead of input x squared, output 9 that we had in the original. Natural log of 9 is just some number, so I can finish this solution just by saying that x is plus or minus the square root of the natural log of 9. The final equation on this page has a secant in it, which at first seems awful, and then you realize, well, secant is just 1 over cosine. So this equation is the same thing as saying 1 over cosine of x, 1 over cosine of 3x is equal to 4, and we know that means that the cosine of 3x must be 1/4. like I've been doing in class, I will use theta for 3x, just to save my sanity. One solution of this is going to come from the inverse cosine function. So the inverse cosine of 1/4 is going to give me one solution to this equation. So I have to punch this in my calculator. Calculator says the inverse cosine of 1/4 is approximately 1.318. The symmetry tells us that another answer will be 2 pi minus that, 1.318. That'll give us another solution that is approximately 4.965. But each of these will have plus 2 pi k. And it's important to get those in there at this point because that's what the period of the cosine function is 2 pi. But that means that, remember, theta is not really the variable we're solving for, x is, and 3x is what's standing, or what theta is standing in for. So we mean that 3x is 1.318 plus 2 pi k. And we mean that 3x is 4.965 plus 2 pi k. So in order to solve for x, I need to divide both sides of these equations by 3, and I do have to divide each thing by 3. So when I do that, 1.318 divided by 3 will be 0.439, and now instead of plus 2 pi k, I'll have a third of that, 2/3 pi k. So this is one possible set of solutions. And then I have to do the same thing for this other one. I don't think I have room to do it, but I'll squeeze it in down here. The x here will be approximately a third of 4.965, which is about 1.655 plus 2/3 pi k. So we'll make sure we divide everything in the equation by 3 to get our solution for x.